Greetings and welcome to another exciting Extension 1 class. Today we're going to be looking at a more complex formula for exponential growth and decay. Now herein lies our biggest problem. In advanced maths, there is an exercise called 6.3 that talks about exponential growth and decay. And today we're going to be doing more complex questions when we haven't even looked at or discussed what the basic questions are. So an extremely quick overview is this. Imagine you have a quantity of something. It doesn't really matter what it is. So let's say we have a quantity of something and it's changing over time. Let's say that quantity was a population. So Q could stand for a population. dQ dt is how the population is changing over time. We say that the way a population changes over time can be proportional to what the population is. In other words, if you have a massive population, the way that changes over time could be very different to a really small population. Now, we actually haven't spent much time at all talking about this concept in maths. They don't tend to talk about it nowadays, but that's being proportional to. And when you have something that's proportional to, we can actually get rid of that proportional to statement, put an equal sign, and we introduce what we call a constant of proportionality. Now we'll spend a lot more time talking about this in advanced, but that is the overview of the simple version of exponential growth and decay. And when you have something changing over time is equal to some constant multiplied by the original amount, that transfers to the following formula. And again, we'll talk about that in advanced maths, but that is our formula for exponential growth and decay. So let's see what happens if we try exercise 6.4, realizing that we have a formula for exponential growth and decay, and it's basically just linking a quantity to itself, the way it changes. So here is our more advanced approach. We know dq dt equals kq is a simple approach. Instead of calling it q for quantity, we're going to call it n for quantity or number or amount, or it doesn't really matter. If n has a rate of change, it's proportional to the difference between n and p. There's the difference between n and p. So if n has a rate of change, that means the derivative of n, there it is, there's n with a rate of change. It's proportional to, we put an equals with a k, that gets rid of the proportional sign. It's proportional to the difference between n and p, there's your difference between n and p. We actually have a statement that is a much more advanced statement for exponential growth and decay. And that can actually change to n equals p plus ae to the kt, where P and N are the difference between the two things that we started with. N could be a temperature and P could be room temperature, and the temperature changes over time and room temperature is constant. Could be something like that. We'll do some examples and hopefully that'll make more sense. This formula is actually used in physics and it's used for population growth situations. Newton's law of cooling also uses it. Now the proof is a strange one. The actual proof for advanced maths is a little bit easier, but the proof for advanced maths has been on HSC exams probably 4 or 5 times in the history of the HSC that I can recall. This is the proof for the more advanced one. So what we need to understand is this. We have dn dt, that is our, so we basically got this statement here. That is our change of our value of n over time. It's equal to k n minus p, the difference between n and p. Now, we're told that that is what it's equal to. So that's why this is a strange proof, because we're actually going to start with the answer. Whoops, let's not write it like that. So it's p plus a e to the kt. So we actually start with our answer, if you like, and we're going to do something to it. we have our statement here. Here it is. We're going to differentiate both sides. So the derivative of n is dn dt. We differentiated n with respect to t. The derivative of p, that gives 0. The derivative of ae to the kt, this is a power of e. So when we're differentiating, we write down the derivative of the power, which in this case is k, and we multiply that by the question. And then we say this, and this is going to seem a bit strange, and we'll talk about it later. Where ae to the kt is equal to n minus p. Now how do I know that? How do I know that's true? Well, let's look up here. What would happen up here if I minused p to both sides? On the left side I get n minus p. On the right side I'm just left with ae to the kt. So ae to the kt can be rewritten as n minus p, and that has proven our statement. Bit of a weird one. Let's try some questions to see if we can actually make sense of it, and again we can talk about this in class when I get back. So here's our first example. In a certain town, the growth rate in population is given by dn over dt equals k, n minus 125. Show that n equals 125 plus ae to the kt. We've got to show that's a solution. Well, if we're showing that's a solution, we're taking this part here and we're differentiating it. So let's differentiate it. Derivative of n is dn dt. The derivative of 125 drops out. The derivative of ae to the kt, derivative of the power is k, multiplied by the question. But if we look at the original question up here, if I minus 125 to both sides, I end up with this. Minusing 125 to both sides, I get this. Which means another way of writing ae to the kt is n take 125. So here I can say that's k, instead of ae to the kt, it's n take 125. So we can therefore n equals 125 plus ae to the kt, that's what we were asked to show, is a solution to the equation. If you got an exam question like that, it'd be only worth 1 mark. It's straight differentiation, substitute back in, that's all it is. So that's showing that it is a solution. Let's actually answer something that's more meaningful. If the population is initially 25,650, I'm not even going to keep going. I'm going to pause there for a moment. I'm going to write this down. Initially is at time equal to 0. So at time 0, our population is 25,650. That's what the question is actually telling us initially. Now the next thing we need to do is keep reading. If the population is initially 25,650 and after 5 years it's 31,100, well that means after 5 years, when t is 5, the population is 31,100. Find the population after 8 years. So when time is equal to 8, what is the population? So I've broken that question into 3 separate parts. Let's answer the first part, but looking at part A, we've got a formula, and our formula is n equals 125 plus ae to the power of kt. Now if we use time as 0 and the population is 25,650, what does that actually generate? Well, let's plug it into our formula. Where I see n, I put 25,650 equals 125 plus a e to the k times 0. Anything times 0 is 0. E to the power of 0 is 1. So that part there is just going to become 1 times a, which is a. I'll now minus 125 to both sides. And that will leave me with a being equal to 25,525. So I have a value for a now. That is the value for a for the question for the rest of its life. It doesn't change. So my formula is no longer n equals 125 plus a e to the kt. My new version of the formula is now n equals 125 plus 25,525 e to the power of kt, because I know what a is. Now my second piece of information here, I know that that is when t is 5, the population is 31,100. So I'm going to plug that into my new formula. When the population is 31,100, I get 125 plus 25,525 e to the power of k times 5, which I'll write as 5k. I need to tidy that up a bit, so the first thing I'll do is minus 125 to both sides. If I do that, I'm going to get 30,975 equals 25,525 e to the power of 5k. Well, next, I'm going to divide both sides by 25,525. And that will leave me with, if I cancel 30,975 over 25,525, put that into the calculator, it will cancel down to 1239 over 1025. I'll leave it as a fraction. I don't want to write it as a messy decimal. And that equals e to the power of 5k. Now, we've done some logarithms and exponential work. What I'm going to do now is take this that's written in index form and change it into logarithm form by sliding my base. If I slide that e across, I'll get log to base e of 1239 over 1025 equals 5k. Let's keep following this through. I want to get k by itself, so I'm going to divide both sides by 5. This is a tricky way to write it. If I'm dividing by 5, that's timesing by a fifth. 1, 2, 3, 9 over 1025. Okay, there's my statement that tidies it up. Probably didn't even need to rewrite this line here. I could have just typed this into the calculator and pushed divided by 5. And then I'm going to get an answer for k that I'm actually going to write the entire decimal down. So I get k equals 0.038 7044 1269. We're going to use that full value because that gives us the most accuracy that we can have. The answer is actually longer than that. That's as far as the calculator can actually give us with the number of decimal places the calculator is able to compute at. Now, I have a value for k, which means my formula, and remember, here's my formula. I figured out this number, I now know k. So I'm going to rewrite my formula. So my new version of the formula is as follows. I get n equals 125 plus 25,525 e to the power of k times t, which is 0.03870441269t. That's my new formula. Now, the question says, in the third piece of information up here, when little t is 8, so after 8 years, what's the population? So I'm going to come back here and let little t be equal to 8. And if I do that, I'll get equals 125 plus 25,525 e to the power of 0.03870441269 times 8, which equals, and put that into your calculator, and I got 34913.73633, and that's going to be rounded to about 34,914, we'll say. So what are we saying? For this particular question, we're talking about a town's growth rate of its population. The population of the town was originally 25,650. After 5 years, the population had grown to 31,100, and after 8 years, the population is almost 34,914. Not quite there, but very, very close. Let's continue. Part C says, when will the population reach 40,000? So, when will it reach 40,000? Well, remember our formula, because I don't have it on the screen anymore. Our formula is n equals 125 plus 25,525 e to the power of 0.03870441269t. When will the population reach 40,000? Well, put in 40,000 for the population. Minus 125 to both sides. And if we do that, we will get 39,875 equals 25,525 e to the power of, this is painful writing this all out, but we need to keep things as accurately as possible, as accurate as possible. Now, I'm going to divide both sides by 25,525. When I divide both sides by 25,525, it's going to cancel to 1595 over 1021 on the calculator. Slide our bases, so log to base e of divide both sides by 0.03870441269. So put this into your calculator, then divide by that, and you will end up with t equals, to three significant figures, if you look at it on your calculator screen, 11.5, and that's in years. So after 11.5 years, the population is going to be 40,000 people. Right, let's try our second example. Hopefully we'll start to make more and more sense as we go. A saucepan of water is heated to 95 degrees Celsius. So we've got water at 95 degrees Celsius. Room temperature is a constant 23. The water cools down to 55 degrees after 5 minutes. The cooling rate is proportional to the difference in the water and the room temperature. That's what makes the exponential growth or decay, in this case decay, take place. Show the equation for the water temperature is given by, so temperature equals 23, that's the constant room temperature, plus 72, we'll have to sort that out, e to the minus 0.162 T. Okay, let's figure out what we actually know. This is what we know. When we start at time 0, the temperature of the water is 95 degrees Celsius. We also know that 5 minutes into our experiment, the temperature of the water is 55 degrees Celsius. So let's use those values and see what we can actually generate. Now, because this is an exponential growth and decay with a fixed room temperature, we need our starting statement. The starting statement is the temperature will equal P plus A e to the kt. Remember, P is our fixed constant, which in this case is the room temperature. Now, what we'll do is we'll plug these values in that we know. We'll say when t equals 95, little t, when time equals 0, the temperature is 95. So we're going to put this information in. When time is 0, the temperature is 95 and room temperature is 23. So they're the pieces of information we're putting in initially. So we'll get 95 equals room temperature plus A e to the k times 0, which is 0. Anything to the power of 0 is 1, so that drops out. Minus 23 to both sides. 95 take away 23 is 72. Now I know the value of A, which is 72. That means my new formula is now this. T equals P, I know P is 23, plus, oh I know A is 72, I just found that, e to the power of kt. So let's plug in this information here. When the temperature, after 5 minutes, the temperature is 55 degrees. So when the temperature is 55 degrees, I get that. Minus 23 to both sides. 55 take 23 is 32. Oops, not kt, it's now 5k, sorry. Divide both sides by 72, and 32 divided by 72, I'm going to cancel that down. It cancels down to 4/9. So 32 divided by 72 equals e to the power of 5k, and we get that. Now, slide the bases, so I get log to base e of 4/9 equals 5k. So, put this into your calculator, natural log of 4/9, and then divide it by 5, and you'll end up with k equals minus 0.16218604332, and the question only wants us to take it that far, so we can say therefore t equals 23 plus 72 e to the power of minus 0.162 t. It's happy to write that to 3 decimal places for this question. So there's part A sorted. Find the temperature of the water after 30 minutes. Well, our formula, quickly write that down again. There's our formula. After 30 minutes, that means let little t equal 30. And if I do that, I do 23 plus 72 e to the minus 0.162 times 30. Now when I put it into the calculator, I didn't use minus 0.162. I used the full decimal answer from part A, and you'll get something very close to 23.55 degrees. That's what the temperature is after 30 minutes. Let's keep going. When will the water temperature reach 30 degrees Celsius? Give your answer to one decimal place. Well, we know our formula. Got to write that again. There's our formula. So when will the water temperature reach 30 degrees? Well, that means we want the temperature of the water to be 30. Minus 23 to both sides. Divide both sides by 72. Slide our bases. Calculate the natural log of 7 over 72 and then divide it by minus 0.162, and you'll get an answer that's very close to 14.4, and this is in minutes. So after 14.4 minutes, the temperature will be 30 degrees. Part D. Show the temperature of the water approaches 23 degrees as T approaches infinity. So let's remember our formula. T equals 23 plus 72 e to the minus 0.162 t. As T approaches infinity, what's happening? Now, what I could do is I could actually put into the calculator 23 plus 72 e to the minus 0.162 times 9999999, push equals, and just have a look at what the answer is close to, because that's all I'm after. But if I wanted to explain it in a more complicated way, I could say, if I was focusing on this part here that I've just put a circle around, as T approached infinity, that would become e to the minus 0.162 times a huge number, a really big number. Now, if it's times a really big number, minus 0.162 times a huge number is heading towards e to the power of a negative big number. And if you put e to the power of any huge number, the answer is getting closer and closer to 0, which means this equation that we have, T equals 23 plus 72, that circle part there is getting closer and closer to 0. So it's getting closer and closer and closer to being 72 times 0. 72 times 0 is 0, which means 23 degrees is what the temperature is heading towards. So as the water approaches 23 degrees as time approaches infinity. Let's try example 3. Our last one. A loaf of bread at a temperature of 20 degrees Celsius is placed in a freezer whose temperature is a constant minus 15. Okay, so what do we know originally? Let's write down what we know. We know that at time 0, the temperature of the bread is 20 degrees Celsius. Okay. I need to create an equation. I know this is, well, let's see what else. If it takes 18 minutes for the bread to drop to 8 degrees Celsius, that means after 18 minutes, the temperature of the bread is 18 degrees Celsius. How much longer to the nearest minute will it take for the bread to reach 0 degrees Celsius? So, how long will it take for the bread to get to 0 degrees Celsius as it's sitting in this freezer? Well, let's start with our formula. The temperature of the bread is going to equal the fixed room temperature, or in this case, the fixed freezer temperature, plus AE to the KT. That's our formula. Let's use the first piece of information. At time 0, the temperature is 20 degrees. So we plug that in. 20 degrees will equal minus 15 plus AE to the 0. That drops out because anything to the power of 0 is 1. Plus 15 to both sides. I now know the value of A for my formula. So let's rewrite the formula. T equals minus 15 plus 35 e to the power of KT. Well, let's use our second piece of information. This part here. We know that after 18 minutes, the temperature is going to be 18 degrees Celsius. Oh, need to be careful, and you've probably been looking at it. Very careful with that. After 18 minutes, the bread drops to 8 degrees Celsius. So let's fix that up there. That's better, because after 18 minutes, it's 8 degrees Celsius. Righto, now that we've fixed that, let's keep going. That becomes 8. Using this information here, we'll get 8 equals minus 15 plus 35 e to the power of k times 18, which is 18k. Let's plus 15 to both sides. 8 plus 15 is 23. Divide both sides by 35. Take the natural log by sliding the bases. Take the log of 23 over 35, the natural log of 23 over 35, and divide by 18, and we generate k is equal to minus 0.02332521364. Wow, that's our value of k now. Well, let's put that in our formula. Our formula becomes T equals minus 15 plus, we know what A is, that's 35. E, do we know what K is? Yes, minus 0.02332521364 T. Now the question asks us, when will the temperature get to 0 degrees Celsius? At what time? So it's at 0 degrees Celsius when capital T is 0. .02332521364T plus, I'm going to do 2 steps in one line here. I'm going to plus the 15, then I'm going to divide by 35 to both sides. Hopefully you understand what I'm doing there. Now I'll slide the base, so I get the natural log of 15 over 35. Now that cancels, but it doesn't matter. The calculator will take care of that. So, take the log of 15 over 35, or 3/7 if you wanted to cancel it, divide it by this decimal here, and you'll get t equals approximately 36.3, which is minutes. So the bread should be at 0 degrees Celsius after 36 minutes approximately, or 36.3 minutes if you want to be more precise. 36 if you're going to the nearest minute. That's the process. Hopefully you can understand what's going on. We'll talk more about it when I get back. Try and do the questions and enjoy. Bye for now.